Water once flowed uphill to keep empires alive. This is the story of the gravity-defying aqueducts, stone arteries that conquered mountains to bring life to thirsty cities. By the end, you will understand the three hidden principles that made this ancient magic possible, principles we still rely on today. How did engineers 2,000 years ago calculate a perfect slope across 50 miles of wilderness? What forgotten material allowed them to force water up the side of a valley? We will uncover the precise mix of genius and grit that turned an impossible idea into flowing reality. What does it mean to build something meant to outlast your civilization by 1,000 years? A hilltop city in the ancient world was a fortress of safety and a prison of thirst. While the high ground offered protection from invaders, it created a desperate hydrological paradox. The very springs that first drew settlers to the spot could never hope to quench the needs of a thriving metropolis. As populations swelled into the tens of thousands, local wells ran dry and streams became contaminated. The people and the empire they represented faced a quiet crisis. A city without abundant, clean water was not merely uncomfortable, it was unsustainable. Public health, industry, and the very social fabric depended on a constant, clean flow. This was not a luxury, it was an existential demand. The solution, however, lay far away in the pure mountain watersheds, separated by miles of treacherous, uneven terrain. Gravity was the immutable enemy. Water, left to its own devices, always seeks the lowest point. To bring it from a distant mountain spring into the heart of a city built on hills meant convincing that water to do the one thing it naturally refuses to climb. For the engineers of Rome, tasked by emperors and demanded by the public, this was the supreme technical challenge of their age. They were not just plumbers, they were urban alchemists, tasked with transforming geographic impossibility into civic reality. The political will was immense because the reward was civilization itself. Reliable water meant public baths that promoted hygiene, magnificent fountains that displayed power and provided gathering places, and a sewer system that carried waste away, preventing illness. The commissioner of Rome's water, a man named Frontinus, wrote detailed records treating the aqueducts not as wonders, but as the essential, working arteries of the city's body. The question was never whether to build, but how. How do you make water defy its own nature? The answer would not be found in a single brilliant trick, but in a masterful application of three profound principles, beginning with a deceptively simple concept, the secret of the constant, whispering slope. The principle that unlocks this first defiance of gravity is found in your kitchen. A simple straw allows you to draw liquid upward, not by pulling, but by creating a pressure imbalance. The Romans scaled this childhood experiment into an engineering marvel known as the inverted siphon. When an aqueduct's path met a deep, wide valley, building a towering stone arcade all the way down and back up was often impossible. The solution was breathtakingly direct. They would take the water channel and turn it into a sealed pipe, sending it plunging straight down the valley wall, across the floor, and then compelling it to climb the far side. The magic wasn't magic at all, it was pure physics. The immense weight of the water column descending the first slope created tremendous pressure at the bottom of the U-shaped pipe. This pressure, harnessed and contained, became the force that pushed the water up the opposite slope. The goal was not to return the water to its original height, that would violate nature's laws, but to bring it out at a point just slightly lower than where it began, maintaining the overall gentle downhill slope of the entire aqueduct system. The true genius and the immense challenge lay in the container. To hold that crushing pressure without bursting required a material revolution. The Roman engineer Vitruvius, in his famous architectural manual, detailed the use of thick lead pipes, joined with meticulous care, or in some cases robust ceramic conduits. These were not mere channels, they were pressure vessels. The city of Pergamon in modern-day Turkey offers a stunning example. Its aqueducts used massive inverted siphons to cross deep gorges, with lead pipes sometimes stacked in multiple lines to increase the volume of flow. But this technology had its limits, dictated by the strength of their materials. The pressure in a siphon increases with the depth of the valley. Too deep a descent, and even lead pipes would rupture. This physical constraint shaped their entire approach to surveying, often forcing them to choose longer, more winding routes that avoided the deepest clefts in the landscape. So the first principle was one of contained force, using the water's own weight against itself to achieve a controlled climb. It was a powerful tool, but it was not the only one, and it could not solve every topographic puzzle. For the longest, straightest runs across rolling countryside, they relied on a far more subtle and visually iconic form of mastery. The true elegance of the system lay not in forcing water upward, but in persuading it to flow down with a patience almost imperceptible to the human eye. This was the second principle, the constant, gentle gradient. Picture a team of Roman surveyors on a windswept hillside, their most critical tool not a complex machine, but a 20-foot-long wooden trough called a chorobates. Filled with water, its surface became a perfect, self-leveling horizon. By sighting along its edge, they could trace an unbroken line of ideal slope across 50 miles of forest, rock, and valley. Their goal was breathtakingly simple and impossibly difficult: to establish a channel that dropped only a few centimeters for every kilometer it traveled. The Aqua, one of Rome's greatest aqueducts, achieved an average gradient of just 0.3%. That means over a full kilometer, the channel descended only about the height of a single step. This was the golden rule: too steep a slope and the water would rush through, eroding the channel walls and arriving in a turbulent, wasteful torrent. Too shallow and the flow would stagnate, allowing sediment to settle and block the precious conduit. The gradient had to be a whisper, a consistent, coaxing pull that kept the water moving steadily and clearly from source to city. To map this invisible line across real-world chaos required a symphony of simple tools. The groma, a cross-shaped sighting instrument on a pole, allowed them to mark perfect right angles and straight lines. Teams of workers would place sighting poles at intervals, the surveyor peering from one to the next, shouting adjustments until a perfectly aligned path was staked across the countryside. Every contour of the land had to be accounted for. If the planned path met a rising hill, they would either curve gracefully around it or, with staggering labor, tunnel directly through it. When they encountered a dip, they would fill it with a solid earthen embankment to maintain the unbroken line. The legendary Pont du Gard in southern France is the ultimate expression of this principle in stone. It is not merely a beautiful bridge, it is a precise gradient machine. The aqueduct channel at its top descends a mere 2.5 centimeters along its entire 274-meter length across the river Garden. The three towering tiers of arches were built to one purpose: to carry that perfectly calculated slope from one hilltop to the next, as if the valley beneath it did not exist. But how could they possibly ensure such precision over such distances before a single stone was laid? The answer lies in a profound understanding of human error. They knew their tools and eyes could deceive them over miles, so they built in a secret allowance, a margin for correction. The channels were always constructed with a floor slightly steeper than the ideal calculated grade. Then, along the entire length, they installed regular settling tanks. As water flowed, it would deposit its grit and sand in these tanks, which workers would periodically clean. But these tanks served a second, brilliant function. At each tank, the water's surface level provided a fixed, true benchmark. If surveyors found the channel was running too high or too low at that point, they could adjust the slope of the next section, subtly steering the water back onto its perfect, whispering path. It was a system that corrected itself. This relentless, millimeter-by-millimeter pursuit of the perfect drop was the silent, unsung hero of the entire endeavor. It transformed the aqueduct from a simple ditch into a predictable, manageable river. Yet, even this masterful control of slope faced a final, formidable enemy, one that could not be surveyed around or bridged over: the crushing, unseen pressure of the mountains themselves. But a perfect slope is meaningless if the mountain itself refuses to yield. The third principle of this gravity-defying system was not about coaxing water, but about conquering earth. When the surveyor's unbroken line met an impassable ridge, there were only two brutal options: go through it or go around it on a sheer face. Both choices demanded an art of construction that bordered on the superhuman, a marriage of stubborn determination and sophisticated underground geometry. The most direct solution was to tunnel. Roman engineers became masters of subterranean excavation, carving channels straight through the heart of mountains. This was not haphazard digging. It was a precise, dangerous ballet conducted by the flickering light of oil lamps. Teams of workers, often soldiers or enslaved laborers, would begin from both sides of a ridge, aiming to meet in the middle. To keep the tunnel on course, they used the same sighting techniques as above ground, but now in a cramped, dark, and dusty world. Pliny the Elder recorded tunnels so long that builders had to dig vertical shafts down from the mountaintop at intervals. These shafts served a dual purpose. They provided crucial ventilation for men working by fire and hammer, and they allowed multiple digging teams to work on different segments simultaneously, hauling rock and debris straight up and out. The method for breaking the rock itself was ancient and visceral: fire setting. Workers would build a fierce blaze against the rock face, heating it until it glowed, then suddenly douse it with cold water or vinegar. The thermal shock would cause the stone to fracture and crack, making it easier to chip away with iron picks and chisels. It was a slow, smoky, and perilous process, filling the tunnels with noxious fumes and the constant risk of collapse. Within these man-made caves, the Romans often lined the walls with brick or stone and capped the channel with a graceful arch, a signature of their engineering that distributed the mountain's weight and prevented cave-ins. The most astonishing example of this subterranean precision is not Roman, but Greek, predating them by centuries. On the island of Samos, in the 6th century before the Common Era, the engineer Eupalinos directed the carving of a tunnel over 5.5 kilometers long for an aqueduct. What makes it a marvel is not just its length, but its accuracy. Two teams starting from opposite ends of a mountain dug toward each other. When they met, their alignment was off by less than a meter vertically and only a few meters horizontally over that vast, pitch-black distance. It remains one of history's greatest feats of geometric surveying. When tunneling was impossible, perhaps due to unstable rock or an overwhelming ridge, the only alternative was to cling to the outside. Engineers would carve a narrow shelf, a specus, directly into the cliff face. Picture a stone canal just wide enough for a person to walk through, etched into a vertical rock wall hundreds of feet above a valley floor. Building it required workers to be suspended by ropes, cutting handholds and footholds before they could even begin to carve the channel itself. It was work that tested nerve as much as strength. The human effort behind these passages is almost beyond comprehension. The labor was immense, the conditions were brutal, and the risks were ever present from rockfall, asphyxiation, or a fatal misstep. While historical records focus on the engineering triumph, they offer only glimpses of the human cost, the loss of life that was an accepted part of such monumental projects. We can acknowledge this hardship not to diminish the achievement, but to understand its true scale. These were not machines that built the aqueducts, they were people. Their collective effort, driven by command or necessity, transformed solid rock into a conduit for civilization. With the path carved through the most stubborn obstacles, the water now had a clear, engineered riverbed from mountain to city. But the journey was not yet over. A final, invisible challenge awaited, one that could silently strangle the entire system from within. Yet even the most perfectly carved channel is useless if it cannot hold a single drop of water. The silent, final challenge was not the path but the vessel. With the route secured through tunnel and over bridge, the engineers faced a more intimate puzzle. What material could contain this precious flow for a century or a millennium? Their choices were not arbitrary, but a profound dialogue between the landscape's demands and the properties of stone, metal, and mortar. In the sun-drenched stretches of Spain, the answer was granite. The Aqueduct of Segovia is not merely a bridge, it is a declaration in stone. Its towering arches are built from massive, precisely cut blocks, fitted together without any mortar at all. The channel that runs along its top is a single, continuous groove carved from the same unyielding rock. This was a material choice born of local abundance and eternal ambition. Granite resisted weathering, bore immense weight, and promised correctly to stand for 2,000 years. It was the ideal skeleton for an open-air aqueduct crossing a valley, where the only pressure was the gentle weight of the flowing water itself. But stone has its limits. It is magnificent for gravity-fed channels, but you cannot easily bend a granite block into a pipe, nor could it withstand the tremendous forces inside an inverted siphon. For that, the Romans turned to a more malleable, more treacherous ally, lead. In the workshops of the empire, sheets of lead were painstakingly folded into pipes, their seams soldered with molten lead itself to create a seamless, watertight seal. These pipes could be curved to follow a valley's contour and were strong enough to contain the hydraulic pressure that would shatter stone. The city of Pompeii, preserved by volcanic ash, offers a snapshot of this material mastery in action, with lead pipes still in place within its water distribution system. But this solution came with a heavy, hidden cost. Even in ancient times, observers like the engineer Vitruvius and the physician Galen noted the pale complexion and poor health of lead workers, and speculated about the dangers of lead-lined vessels for drinking water. While the full scale of the public health impact is a topic for historians and scientists, it highlights a stark reality of ancient engineering. Every material choice was a trade-off between function, cost, and consequence. Lead was expensive and potentially harmful, but it was the only material they had that could reliably do the job under pressure. Between the solidity of stone and the flexibility of lead lay the unsung hero of the aqueduct, a humble but revolutionary mortar known as opus signinum. This was not ordinary cement, it was a carefully engineered hydraulic concrete. Craftsmen would mix lime with crushed pottery and brick fragments, creating a coarse, pink-tinged aggregate. When set, this material was miraculously waterproof, resistant to cracking, and could be smoothed into a flawless lining for miles of channel. It was the perfect membrane, sealing porous stone and earthen channels against leaks. Archaeological digs along aqueduct routes often find multiple layers of this lining, evidence of centuries of meticulous maintenance and repair. The choice of material was never just about physics or chemistry. It was dictated by the empire's reach. In the heart of Italy, travertine stone and lead from Spanish or British mines might be used. On the frontiers, engineers adapted, using local sandstone or even hollowed-out wooden logs for short sections. The true mastery was this adaptability, this deep understanding that to make water flow forever, you had to build with what the land provided and with a keen eye on the relentless passage of time. Yet, once this river of stone and lead reached the city walls, a new question arose. How do you distribute a mountain's worth of water to 1 million thirsty people? The aqueducts stand as monuments, but their builders remain mostly shadows. We know the names of a few, like the engineer Vitruvius, whose 10-volume work on architecture became the empire's textbook. Yet for every named architectus, there were thousands of unnamed hands and minds who turned parchment plans into enduring stone. This was not a single act of genius, but a colossal symphony of coordinated labor, a social machine as meticulously engineered as the channels it built. At the top was the architect, the master of all arts, responsible for the overall vision, budget, and approval from the emperor or senate. Beneath him worked the surveyors, the librators, with their chorobates and gromers, translating that vision into a precise line on the land. Then came the specialized foremen, the masters of stone cutting, carpentry, and hydraulics, who understood how to shape an arch or seal a lead pipe. And finally, the vast engine of labor itself, a tiered world of status and skill. At its base were the enslaved, providing the brute force for digging trenches and hauling stone. Alongside them, and often in better conditions, were the soldiers of the Roman legions. When not at war, their discipline and engineering training were invaluable for massive public works. They built roads, forts, and aqueducts, their labor a form of tax paid to the state. And there were the skilled freemen, the masons, plumbers, and carvers, who commanded higher wages for their craft. Pay records from sites like the Aqua near Rome show a complex economy, with workers paid in coin, food, and wine, their rates varying sharply by skill. Tomb inscriptions offer rare, poignant glimpses into individual lives. One commemorates a freedman named Lucius, a hydraulic engineer who rose from enslavement to a position of responsibility. Another marks the resting place of a surveyor, proud of the straight lines he laid across the countryside. These fragments remind us that this was not an anonymous force, but a collection of individuals with stories, families, and pride in their work. Coordinating this army across 50 miles of wilderness was a logistical triumph that rivals the engineering. How did they feed thousands of men in remote locations? How did they manage the supply chain for millions of tons of stone, lead, and timber? They pioneered project management techniques we would recognize today. Work was divided into manageable sections, each with its own camp and overseer. Materials were sourced locally where possible, or shipped via river and road in a continuous flow. Messengers on horseback kept site managers in communication with central command. The entire operation ran on a detailed schedule with penalties for delays. This organizational genius, the ability to marshal and sustain human effort on a geographic scale, may be their most underrated innovation. It was the quiet framework that made the loud miracles possible. The true magic was not in defying gravity with a single brilliant device, but in aligning the hopes, muscles, and minds of countless unknown people toward a single, flowing purpose for generations. Rome's first aqueduct arrived not with a parade, but as a necessity of war. In the year 312 before the Common Era, the censor Appius Claudius Caecus commissioned a channel to bring water from springs over 10 miles away into the growing city. The Aqua Appia was largely an underground trench, a practical and defensible solution, but it marked a turning point. Water was no longer just a local resource, it was an urban utility to be imported by the will of the state. Over the next 5 centuries, that single channel would grow into a sprawling hydrological network, the ultimate expression of Roman engineering ambition. By the height of the empire, 11 major aqueducts fed the capital, their combined length stretching over 260 miles. Each new aqueduct was a response to growing demand, a trophy of a conquering general, or a gift from an emperor to his people. They were not built as a unified plan, but as layers of infrastructure, one atop the other, a stone chronicle of the city's expansion. The Aqua Claudia, begun by the Emperor Caligula and finished by Claudius in the 1st century, stands as the archetype of this mature system. It was a masterpiece of integrated solutions. For most of its 40-mile journey from the cool springs in the hills, it ran in a dark, cool tunnel underground, protected from evaporation and enemy sabotage. But when the terrain demanded spectacle, it emerged into the light on soaring arcades of brick-faced concrete, marching across the Roman countryside like a colonnade for a river. At points, it employed inverted siphons to cross deep depressions. The Claudia was a hybrid, using every tool in the engineer's kit. Its end point was the most critical of all, the massive distribution tank at the Porta Maggiore, where its waters were mingled with those of another aqueduct, the Anio Novus, before flowing into the city's heart. To understand the scale of this achievement, we turn to the meticulous records of Sextus Julius Frontinus, the water commissioner appointed near the end of the 1st century. His book on the aqueducts of Rome is not poetry, it is a technical audit. He measured everything. According to Frontinus, the 11 aqueducts delivered over 1 million cubic meters of water to the city every single day. That is enough to fill a modern Olympic swimming pool more than 400 times each day for centuries. This volume was not simply dumped into the Tiber. It was carefully allocated through a brilliantly organized distribution system. From the main terminal tanks, water flowed through lead pipes of calibrated sizes to public basins, to the imperial palaces, to the barracks of the army, and for a fee to the private homes of the wealthy. Priority was absolute, first for public health and safety, then for public display, then for private use. The countless public fountains or lacus ensured no citizen, rich or poor, was ever more than a short walk from fresh water. This network was the bedrock of Roman civic identity and health. The public baths, like the immense baths of Caracalla, were not mere luxuries. They were social hubs and temples to cleanliness, consuming vast quantities of water. The continuous flow flushed the city's sewers, most famously the Cloaca Maxima, carrying waste away and mitigating disease in a crowded metropolis of over 1 million people. An aqueduct was the ultimate symbol of civilized life, a literal flow of order conquering the chaos of nature. Its maintenance was a sacred imperial duty. Frontinus himself describes clearing illegal private taps and repairing channels clogged with mineral deposits, a never-ending battle against neglect and fraud. The system did fail, sometimes catastrophically. Channels could collapse from poor maintenance or be severed by invaders. Repairing an aqueduct was an emergency operation, often funded directly from the emperor's treasury, because a city without water was a city on the brink of riot. Each repair, each new emperor adding his own aqueduct, reinforced the same message: the state exists to sustain the life of its people. Rome's water network was a circulatory system, and its steady pulse was the sound of empire itself. Across an ocean and a world of context, another civilization faced a water crisis defined not by hills, but by absolute absence. The coastal desert of southern Peru is one of the driest places on Earth, a landscape where rain might not fall for a decade. Here, the Nazca culture thrived for centuries, famously creating the vast geoglyphs etched into the desert floor. But their true genius for survival is not written on the surface. It is hidden beneath it in a network of spiral stone wells called Puquios. These were not aqueducts that crossed mountains, but gravity-defying instruments that reached down to coax a hidden river into the light. While Roman engineers mastered the long horizontal journey, the Nazca solved the vertical puzzle, accessing water that lay trapped deep within the earth. The Puquios are elegant in their simplicity and profound in their understanding of the desert's hidden mechanics. They begin with a horizontal tunnel, carved with stone tools through the hard desert subsoil, often for kilometers. This tunnel or filtration gallery was angled to gently intercept the underground water table, the aquifer, allowing precious water to seep into its channel. But a tunnel deep underground is a tomb for air, and without ventilation, workers could not breathe and water would not flow. This is where the signature spiral enters the story. At regular intervals along the tunnel's path, the Nazca builders carved vertical shafts up to the surface, but these were not simple holes. They were constructed as descending stone corkscrews, open spiral ramps that wound down into the darkness. Their brilliant function was as a natural pump. The desert winds, constantly sweeping across the plain, would catch in these open spirals. As the wind spiraled downward, it created a flow of air that pushed into the horizontal tunnel, ventilating it and, critically, creating a slight atmospheric pressure difference. This gentle push helped draw the seeping groundwater along the tunnel, encouraging it to flow toward the collection points. It was a passive, energy-free system powered entirely by the desert's own breath. The water, once gathered, was then channeled through open canals to fields and settlements, transforming barren valleys into green, productive oases. The ongoing mystery of the Puquios is not their function but their origin. Unlike Roman projects, there are no imperial records, no engineer's name like Frontinus to give us a date. The Nazca left no written language. Archaeologists and historians debate their age fiercely, with estimates ranging from over 1,000 years before the Common Era to around 500 years into the Common Era. Some researchers suggest they were built in response to a prolonged period of intensified drought, a monumental community effort to adapt to a changing climate. This debate makes them more fascinating, not less. They stand as a testament not to a single emperor's decree, but to a society's collective will to survive and flourish against environmental odds. What do these spirals in the sand tell us about adaptation? They reveal a deep, localized intelligence, an innovation born from intimate observation of wind, geology, and water. The Romans imposed order on geography with monumental force. The Nazca collaborated with hidden forces using subtle, sustainable design. The Puquios were maintained and used for over a millennium, and some are still in use by farmers today. They represent a different kind of defiance, not conquering gravity across a landscape, but partnering with the very elements of a harsh world to reveal a secret, sustaining flow. This ingenuity raises a final, haunting question. As these ancient systems fell silent, what became of the knowledge that built them, and what echoes of their failure might we hear in our own time? Constantinople was a city designed to be unconquerable, yet its greatest vulnerability was not its walls but its thirst. Perched on a triangular peninsula, the new capital of the Eastern Roman Empire had no major rivers within its boundaries. Its survival and the endurance of an empire that would last another 1,000 years hinged on a single, audacious act of engineering, importing a river from the wilderness. While the Aqueduct of Valens is the iconic stone spine marching through the modern city center, it was merely the final conduit of a far more ambitious network. The true lifeline began over 120 kilometers away, in the dense Belgrade forest north of the city. Here, pure springs were captured and channeled into a system so vast and resilient it defied not just geography, but time and war itself. To understand its scale, stand before the ruins of the Balacerm Bridge in modern-day Turkey. This is not a delicate arch, it is a muscular statement in stone. Its 2 tiers of arches stride across a deep valley, carrying the water channel 90 meters above the riverbed below. Building it required a mastery of geometry and mass production. The arches were constructed from standardized, precisely cut blocks, allowing teams to work on multiple sections simultaneously, a modular approach that sped construction in a race against political urgency. The historian Procopius, chronicling the building campaigns of the Emperor Justinian in the 6th century, wrote of these projects not as luxuries but as vital organs of the state. He describes crews of soldiers and laborers carving channels through solid rock and raising bridges that seemed to stitch the landscape together. Their goal was to create a flow so reliable it could withstand the ultimate test, a siege. Constantinople's genius was in its redundancy. The long-distance aqueducts did not empty directly into pipes, but into monstrous subterranean reservoirs. The Basilica Cistern, with its forest of recycled classical columns, is the most famous, but it was just one of hundreds. These cisterns, scattered across the city, held a strategic reserve of water that could sustain the population for months if the aqueducts were cut by an enemy. This transformed water security from a civic concern into a core military strategy. The city could not be starved into submission as long as its hidden oceans lay beneath the streets. Ensuring these structures lasted required another innovation, a mortar of legendary strength. Byzantine engineers perfected a formula using crushed brick and ceramic dust, creating a hydraulic concrete that could flex slightly without cracking. This was the silent guardian against Constantinople's constant companion, earthquakes. The mortar acted as a shock absorber, allowing arches and cistern walls to sway and settle without catastrophic failure. It was this combination of grand vision and microscopic material science that gave the system its millennial lifespan. The water's arrival fundamentally shaped the city's heartbeat. It fed public baths that served as social centers, supplied countless neighborhood fountains, and enabled the lavish gardens of the Great Palace. More critically, it allowed for dense urban planning. With a secure water supply, population could concentrate safely behind the land walls, enabling Constantinople to become the largest, most fortified city in the medieval world. The aqueduct was not merely a utility. It was the central artery of an empire's resilience, a physical manifestation of the Byzantine ideal to endure through adaptation and monumental foresight. Its legacy poses a quiet question for our own crowded cities. What does it mean to build infrastructure not just for convenience but for survival? The silent precision of these structures speaks of a hidden language, a mathematics carved not in chalk but in stone and water. To build a channel that drops only a hand's width over a mile, or to calculate the exact diameter of a lead pipe to serve 10,000 people, required a numerical fluency we rarely appreciate. They achieved this without a single zero in their numeral system, without calculators, without even the consistent use of parchment for complex diagrams. Their mathematics was a physical, embodied craft. It began with the most fundamental tool of all, the geometry of sight. Surveyors relied on the unchanging truths of similar triangles. By setting up a simple right-angled triangle with known dimensions on a small plotting board, they could use it to extrapolate measurements across vast distances. If they knew the height of a distant hill and the angle to its peak, measured with a simple sighting instrument, the proportional relationships of the triangle gave them its distance. This was not abstract theory, it was a repeatable recipe for mapping the world. The groma, that cross-shaped sighting tool, allowed them to extend these perfect right angles across the landscape, creating the straight lines and perpendicular offsets that defined the aqueduct's path. Every stake driven into the ground, every trench started, was the physical manifestation of a geometric proof solved in the dirt. The calculations continued once the path was set. The volume of water a channel could carry, its quinaria, was everything. Engineers calculated a channel's cross-sectional area with remarkable care. Vitruvius gives specific ratios for optimal channel proportions, wider than they were deep, to maximize flow while minimizing friction against the walls. They understood that a semicircular channel, while using more material, created a smoother, faster flow than a square one. This was applied mathematics, born from observation and refined through generations of trial and error. For pipes, the rules were even more precise. Pipe sizes were standardized, with names like the quinaria or the centenaria, based on their cross-sectional area. Frontinus's entire treatise is filled with complaints about the confusion when local plumbers used mismatched standards, because the math of water delivery was unforgiving. A pipe too narrow for its length and the pressure behind it would burst. A pipe too wide and the water would slow, allowing sediment to choke it. They developed empirical formulas, likely passed down as oral tradition in guilds, relating pipe diameter, pressure from the source, and expected delivery volume. The theoretical underpinnings of this fluid dance were explored by thinkers like Heron of Alexandria. In his work Pneumatica, Heron described the principles of siphons and water pressure, even detailing clever devices like a primitive steam engine. While it is unlikely that every aqueduct foreman read Heron, his work represents the codification of principles that practical engineers were already using. Heron understood that air was a substance that could be displaced, that water sought its own level, and that pressure in a closed vessel was uniform. This knowledge informed the daring inverted siphons, where calculating the pressure at the bottom of the U was a matter of structural survival. Translating these abstract numbers and ratios into the physical world was the final, brilliant leap. They used ropes knotted at precise intervals for measurement, bronze measuring rods, and calibrated vessels to check water volume at distribution tanks. Most importantly, they built in constant checkpoints. The regular settling tanks were not just for cleaning, they were data points. The water level in each tank told the engineers if their calculated slope was holding true in reality. If the level was too high, the channel ahead was too steep, wasting water. If it was too low, the channel was too shallow, risking a blockage. They would then adjust, a continuous feedback loop of calculation, construction, and correction. This was a proto-engineering science, a discipline where mathematics was not separate from the hammer and chisel, but was the very thought behind them. It proves that precision is not a product of technology, but of meticulous method and a deep, physical conversation with the material world. That mathematical conversation did not end with the last Roman engineer. The principles of moving water against its will became a kind of intellectual inheritance, flowing through the centuries and re-emerging wherever civilization faced the same thirst. The fall of Rome did not break the aqueducts, but it did scatter the knowledge which found new life in unexpected places. In the arid landscapes of Persia, a different but equally brilliant solution had existed for millennia: the Qanat. These were underground tunnels that tapped into mountain aquifers and used gravity to deliver water to the surface many miles away, all without a single pump. When Islamic engineers absorbed the territories of the former Roman and Persian empires, they inherited a dual legacy of hydraulics. During the Islamic Golden Age, scholars in places like Baghdad and Cordoba did not just preserve Roman texts on engineering, they expanded upon them. They built intricate water-raising devices, sophisticated irrigation networks, and public fountains that turned courtyards into oases, applying precise mathematical principles to an art they saw as both practical and divine, a way to manifest paradise on earth. This pooled knowledge eventually seeped back into a reawakening Europe. Behind the high walls of medieval monasteries, you can see the aqueduct's legacy in miniature. Isolated communities of monks dedicated to self-sufficiency became masters of small-scale hydraulics. They would channel spring water through clever networks of wooden or lead pipes, using the natural slope of their land to supply fountains, kitchens, gardens, and even early sanitation systems. Their work was a quiet, practical echo of the Roman civic machine, proving the core ideas could thrive on any scale. The true renaissance of this ancient science, however, came with figures like Leonardo da Vinci. Obsessed with the movement of water, he filled his notebooks with studies of Roman siphons, whirlpools, and canal locks. He sketched designs for improving urban water supplies and even envisioned a subterranean, two-level city to manage traffic and water flows separately. Leonardo was not just an artist dreaming of the future, he was an engineer in deep dialogue with the past, trying to decipher and improve upon the monumental work of those who came before him. When the great modern cities of the 19th century faced their own water crises, exploding from industrialization and disease, their engineers turned directly to the ancient model. The designers of London's monumental sewer system and New York's Croton Aqueduct were classically educated men. they saw the Roman aqueducts not as ruins but as textbooks. The specific elements they rediscovered were profound: the absolute necessity of a constant, gentle gradient to maintain flow and prevent sediment buildup, the strategic use of settling basins for purification, and the overwhelming advantage of using gravity as the sole motive force wherever possible. The inverted siphon principle was reinvented for pressurized iron pipes, allowing water to cross deeper valleys than the Romans ever dreamed. What we see is not a straight line of progress but a spiral. A solution is invented, forgotten in one place, preserved or reinvented in another, and then rediscovered with new materials and greater ambition. The 19th century engineers stood on the shoulders of giants, but they also had cast iron, steam-powered excavation, and germ theory. They built for the same reason the Romans did: to prevent illness, to enable growth, and to assert a kind of civic order over nature. This continuity reveals something fundamental: the challenge of water is a perennial thread in the human story. Each generation must solve it anew, but they are never truly starting from scratch. They are drawing from a deep well of accumulated ingenuity, a hydraulic heritage written in stone, parchment, and flowing water itself. Yet for all their genius, these systems held a silent, ticking flaw, a vulnerability not of engineering, but of the very substance they carried. The water has long since stopped flowing, but the conversation is far from over. Today, a new generation of explorers is listening to these stone channels with tools the original engineers could scarcely dream of, revealing secrets hidden for centuries. This is not archaeology with just a trowel and a brush. It is a high-tech dialogue across 2,000 years. The first breakthrough came from the sky. Airborne LIDAR, which stands for light detection and ranging, fires millions of laser pulses at the ground from an aircraft. By stripping away the dense forest canopy that has grown over the centuries, it reveals the ghostly imprint of the aqueduct's path, a straight line etched into the digital landscape, showing where embankments were built and where tunnels begin. This allows researchers to trace entire systems across dozens of miles in an afternoon, work that once would have taken years of grueling survey on foot. On the ground, the investigation goes even deeper without ever breaking the soil. Ground-penetrating radar is like giving the Earth an X-ray. Scientists drag a sled over a field, sending radio waves into the ground. When those waves hit a buried wall or a hollow channel, they bounce back, creating a detailed map of the subterranean world. This non-invasive technique has located lost sections of aqueducts running beneath modern suburbs, revealing how the ancient infrastructure is still silently shaping the city above it. Drones add another perspective, capturing high-resolution photographs and three-dimensional models of surviving arches and bridges. Engineers can then analyze these models for stress fractures and erosion patterns, understanding not just how it was built but how it has aged. One of the most spectacular applications of this modern toolkit is the ongoing study of the Aqua Traiana, built by the Emperor Trajan to supply Rome's western neighborhoods. For centuries, its source and early route were lost to history, buried under landslides and new construction. A multidisciplinary team combining historians, archaeologists, and geologists used LIDAR scans of the countryside north of Rome to identify a suspiciously straight topographic feature leading from ancient springs. They followed this digital clue on the ground, using ground-penetrating radar to confirm the presence of a buried conduit. Their work has remapped the aqueduct's entire course, rediscovering monumental fountain structures and even evidence of medieval mills that later repurposed the Roman waterway. But the analysis does not stop at mapping, it flows into simulation. Using a field of engineering called computational fluid dynamics, researchers can create a digital twin of an aqueduct. They input the precise dimensions of a channel, its slope, and the roughness of its stone lining. The software then simulates the water's behavior. How fast did it flow? How much sediment would it carry? Would it have had enough pressure to supply a fountain at a certain height? These models answer practical questions about the system's daily performance, proving, for instance, that the gentle gradients were not just theoretical. They were meticulously calculated to achieve a specific, manageable flow rate that minimized maintenance. This modern dialogue has solved old mysteries, but it has also raised profound new questions. By calculating the exact volume of water delivered, we gain a startlingly precise understanding of ancient urban population density and industrial activity. We can see where water was prioritized, revealing the social and economic hierarchy of a city. The technology also exposes the builder's mistakes, sections where the gradient was miscalculated and quickly silted up, reminding us that these were human projects, not perfect monuments. The greatest revelation, however, is one of humility. Our lasers and simulations consistently show that the Roman surveyors, with their chorobates and gromers, achieved a level of precision that is difficult to match even with modern instruments over such distances. We are not just studying ruins, we are auditing the work of master engineers, and they are passing the test across millennia. This scientific conversation allows us to appreciate not just the monument, but the mind behind it, a mind now being understood in its own language of mathematics and physics. Yet, as we perfect our understanding of their past, we are forced to confront a parallel from our own present, one written not in stone but in rust and sand. The stone channels brought life to cities, but they also quietly reshaped the very landscapes they traversed. An aqueduct was more than a passive pipe. It was a deliberate re-plumbing of nature, redirecting the lifeblood of entire regions with consequences that rippled out for centuries. To siphon a spring or intercept a river was to make a profound environmental choice, one that ancient engineers understood in terms of immediate need, not ecological balance. The relentless demand of a metropolis like Rome, consuming over 1 million cubic meters of water daily, meant that distant watersheds were tapped and transformed. Springs that once fed local streams and marshes were captured at their source, their waters diverted into the sealed channel. Downstream, the effects could be severe. Historical accounts and modern geological studies suggest some valleys, especially those closer to the city, may have experienced a drop in their water tables. Wetlands that supported agriculture and wildlife could have slowly dried up, pushing rural communities to dig deeper wells or abandon marginal lands. The aqueduct did not just bring water to Rome, it effectively moved the hydrological wealth of the countryside into the urban center, centralizing the resource along with political and economic power. This redistribution created winners and losers on a geographic scale, a form of ancient environmental engineering with a clear human cost for those living in the shadow of the diversion. The builders were also keenly aware of the Earth's restless nature. In regions like Anatolia, rife with seismic activity, engineers displayed a sophisticated understanding of geology. They often routed channels along the sturdy shoulders of hills composed of stable bedrock, avoiding loose, erodible soils that could slip away in a heavy rain. When they had to build across a valley, the placement of bridge piers was a calculated gamble. They sought out natural outcrops of solid rock to serve as foundations, anchoring their arches against both the river's flow and the shaking of the ground. The mortar itself, that flexible, brick-dust concrete, was a seismic innovation allowing structures to absorb tremors without shattering. This was not luck, it was learned resilience, knowledge paid for by the collapse of earlier, less carefully sited structures. The physical footprint of construction was itself a permanent scar. To build the Aqua Claudia, entire hillsides were turned into quarries. Teams of workers would locate a source of good quality travertine or tufa stone, then systematically cut and remove it, leaving behind dramatic stepped cliffs that are still visible in the Roman countryside today. The transport of these multi-ton blocks required new infrastructure, spurring the creation of wide, durable access roads that cut through forests and over hills. These roads, initially built for construction, often remained as permanent features, altering local travel and trade patterns long after the aqueduct was complete. The environmental legacy is complex, posing a difficult question about ancient sustainability. By the standards of their time, these projects were marvels of efficiency, designed to last for ages with minimal ongoing energy input, a stark contrast to our own pump-driven systems. They used gravity, a perpetual and clean force, and built with materials meant to endure for a millennium. Yet, their sustainability was local and linear, focused solely on the enduring service to the city, with little regard for the depleted ecosystems at the source. This is not a failure of their engineering, but a reflection of a different worldview, one where human dominion over nature was the stated goal. Their work forces us to reflect on a trade-off as old as civilization itself, the balance between the brilliant, concentrated light of human achievement and the broader, subtler health of the world that makes that light possible. An emperor did not merely open an aqueduct, he performed a miracle for the public good. The inaugural ceremony was a masterclass in political theater. As the first pure mountain water gushed into a city's central fountain before a cheering crowd, the message was unambiguous. This ruler commands not only armies, but the elements themselves. He provides the very essence of life. An aqueduct was the ultimate piece of state propaganda, a permanent, functioning advertisement for the regime's benevolence and its terrifying technical capability. It demonstrated a triad of imperial virtues: the power to tame chaotic nature, the wealth to fund a decades-long project, and the sophisticated organization to see it through. For the citizen, the soaring arcade marching across the countryside was a daily reminder that the state's reach was long, its will was concrete, and its gift was water. For an enemy or a rival, that same structure sent a very different signal. This civilization could reshape geography to sustain itself indefinitely, making its heartland virtually unassailable through siege. The architecture was never merely functional, it was performative. Compare the approaches of two of Rome's most builder emperors. Augustus, the first emperor, who famously boasted that he found Rome a city of brick and left it a city of marble, understood water as a cornerstone of this transformation. He restored existing aqueducts and built new ones, but his genius was in systematization. He appointed the first water commissioner, creating a bureaucratic cult of maintenance that ensured the flow was eternal. His legacy was one of order and reliable public service, framing the emperor as the careful steward of the people's well-being. A century later, Hadrian took a different tack. An architect himself, he used aqueducts as global statements of Roman identity. In the provinces from North Africa to Asia Minor, he commissioned monumental waterworks. These were not just for utility, they were cultural implants, stone lessons in Roman engineering and generosity, meant to integrate restless territories into the imperial fabric. A local elite in a distant province would drink from a nymphaeum, an ornate public fountain funded by the emperor, and be reminded where their loyalty and their water came from. The message was carved in stone and stamped in metal. Inscriptions on aqueduct arches proclaimed the emperor's name and titles for all eternity. Coins were minted featuring aqueducts on their reverse, with legends celebrating the ruler's provision. A small bronze coin circulating in the marketplace carried the same symbolic weight as the arch overhead, both declaring the emperor as the universal provider. This symbolic power was so potent that it outlived the empire itself. Medieval kings, Renaissance popes, and even modern dictators have all understood the political capital in a public water project. It is a promise made visible, a covenant of civilization written not on parchment, but in the relentless, gravity-defying flow of water itself. The final stone placed was merely the first day of a century-long promise. An aqueduct did not end at its dedication ceremony. It entered a new, more subtle phase of existence, a silent war against decay and disorder fought by an army of specialized keepers. These were the aquarii, the watermen, whose unseen labor was as vital as the engineers' grand designs. Their task was perpetual, a meticulous regime of inspection, cleaning, and repair that transformed the monumental structure from a static wonder into a living, breathing utility. The enemy was relentless. In regions with hard water, a rock-like substance called sinter, or calcium carbonate, would precipitate out of the flowing water and cling to the channel walls. Over years, this mineral crust could thicken to the width of a man's arm, choking the flow to a trickle. Vegetation took root in cracks, its roots prying stones apart. Earthquakes and frost caused subtle shifts, opening hairline fractures. A single neglected breach could drain an entire section, turning a life-giving artery into a useless, muddy trench. Frontinus, in his role as water commissioner, did not just audit volume, he prescribed the cure. His writings detail a maintenance protocol of almost military precision. Teams of aquarii walked the entire length of their assigned aqueduct regularly, inspecting every stretch of channel, every arch, every siphon. They carried simple but effective tools, iron picks and chisels to chip away sinter, brushes and scrapers to clear silt and organic growth. At strategic points, the engineers had installed sluice gates, heavy wooden or bronze barriers that could be lowered to block the flow. This allowed a section to be drained for major repairs. Workers would then descend into the damp, confined channel, often by torchlight, to patch cracks with fresh hydraulic mortar or replace damaged stone blocks. The organization behind this endless work was a marvel of bureaucratic foresight. Maintenance was funded through a combination of state treasury funds and fines collected from those who illegally tapped the system. A dedicated administrative corps managed budgets, scheduled repairs, and kept detailed records. This was not a haphazard reaction to crisis. It was a scheduled, preventative system designed to catch problems before they became catastrophes. The economic logic was undeniable. The cost of constant, minor upkeep was a fraction of the monumental expense required to rebuild a collapsed arcade or redig a silted tunnel. More importantly, it prevented the true cost of failure, an urban crisis. When an aqueduct failed, the effects were immediate and severe. Public fountains ran dry, forcing the poor to queue at dwindling sources. The baths, centers of social life and hygiene, closed. The sewer system's flow slowed, allowing waste to fester in the streets. In a pre-industrial city, this was a direct threat to public order, health, and the perceived legitimacy of the ruling power. History shows us the consequences of neglect. As the Western Roman Empire's central authority fragmented in later centuries, the organized, funded maintenance regimes broke down. Aqueduct channels clogged, arches crumbled, and the life-giving flow to cities like Rome itself gradually diminished. This was not a sudden rupture, but a slow strangulation, a literal drying up of the civic life that the water had sustained. The aqueducts that survived for centuries did so not solely because of the quality of their original mortar, but because generation after generation of aquarii honored the covenant of upkeep. Their quiet, relentless work poses a profound question for any civilization. It is one thing to build a wonder, but are you prepared for the humble, daily duty of keeping it alive? Even the most precise system leaves behind a trail of unanswered whispers. For all our modern scanning and simulation, the aqueducts guard stubborn mysteries, gaps in the record where the logic of the builders disappears into shadow. These are not failures of understanding, but invitations, reminding us that history is less a solved puzzle and more a conversation where we are still learning the language. Take the distribution tanks, the Casella Divisoria. We know they were critical nodes where the main flow was split into smaller pipes for different city districts. But archaeologists have uncovered some with baffling, labyrinthine internal channels, arrangements that seem to direct water in ways that defy any obvious practical need. Were they experimental pressure regulators, attempts to smooth out surges in the flow from distant springs, or did they serve a ceremonial or symbolic purpose we can no longer decipher, perhaps aligning the division of water with a religious calendar or civic hierarchy? The stones do not say. Their silent complexity suggests a layer of hydraulic sophistication, a nuance of daily management that written records never bothered to capture. Then there is the debate over the limits of their most daring tool, the inverted siphon. We can calculate the theoretical pressure based on the height of the descending leg, but what was the practical ceiling? The surviving lead pipes from sites like Pergamon are thick, but could they have handled the pressure of a drop of 200 meters or 300? Some researchers point to aqueduct routes that take extraordinarily long detours around exceptionally deep valleys. Does this prove the siphon's height limit was reached, forcing the engineers to add miles to the route? Or was it a choice based on the sheer cost and risk of manufacturing and burying such a colossal pressurized pipe? Each unfinished or abruptly rerouted channel is a fossilized moment of decision. We find quarries opened and then abandoned, tunnels started and then sealed. Sometimes the reason is clear, an earthquake fault or a layer of unstable sand. Other times the change seems arbitrary. Was it a budget cut from a new emperor, a surveyor's miscalculation discovered too late, or simply a pragmatic adaptation to a local landowner who refused to sell? These odd turns in the stone path are biographies of compromise, showing that even the most authoritarian projects bent to the unpredictable winds of real life. Perhaps the greatest puzzle is not in the stone but in the mind. How did so much detailed, practical knowledge vanish in the centuries after Rome's Western Empire fragmented? It was not a sudden blackout but a slow fading. The centralized bureaucracy that trained engineers and funded the aquarii maintenance crews dissolved. The technical manuals, like Frontinus's, survived in only a few monastic libraries, becoming curiosities rather than textbooks. The knowledge to repair a crack in a pressurized lead siphon, or to recalibrate the gradient of a 10-mile channel, became a lost art because the social and economic system that required that art had changed. A medieval community living in the shadow of a ruined aqueduct might marvel at it as a giant's work, but they would lack the collective organization, the specialized labor, and the mathematical framework to restore it to function. They might repurpose its stones for a castle wall, turning a symbol of public utility into one of private defense. The disappearance of the know-how is a silent testament to how fragile technological civilization truly is, how dependent it is on a web of education, economy, and shared purpose. This is why the field remains so dynamic. Every new scanning technology, every fresh analysis of mineral deposits in a channel, is a chance to ask the stones a new question. The aqueducts are not dead relics, they are dormant witnesses. Their unfinished sections, their mysterious tanks, and their silent stretches across abandoned landscapes are not marks of failure, but dialogues interrupted. They remind us that the past is not a closed book, but a landscape still being surveyed, where each generation, with its own tools and its own questions, traces the line of that ancient, gravity-defying thought once more. A spring was never just a source of water, it was a sacred presence. Before the first stone of an aqueduct was laid, the source itself was already wrapped in story. The Romans believed every clear spring, every rushing stream, was the dwelling of a nymph, a local spirit of place. To tap that water was not merely an engineering act, it was a diplomatic one, requiring rituals and offerings to secure the nymph's blessing for the monumental diversion. This intertwining of myth and mortar was not unique to Rome. Across the ancient world, the act of bringing water was seen as a divine gift, and the engineers who achieved it often blurred the line between mortal and hero. The Greek myth of the river god Alpheus, who was said to have flowed under the sea to reach his beloved spring Arethusa in Sicily, speaks to a deep cultural desire to explain and sanctify the mysterious, underground journeys of water that engineers would later replicate with tunnels. These stories provided a framework for understanding the seemingly impossible, turning a technical project into a shared sacred mission. The Roman god Fons presided over springs and wellheads, his festivals emphasizing purification and the source of life. When an aqueduct delivered water to a magnificent public fountain, or nymphaeum, it was literally bringing the domain of the nymphs into the heart of the city. The fountain was not just a utilitarian in point, it was a shrine, a permanent thank offering to the divine forces that allowed the water to flow. This mythic layer served a powerful social function, convincing thousands of people to labor for decades on a project whose benefits they might never live to see required more than imperial decree. It required a story that placed their effort within a grander, timeless narrative. The legend of a hero or a god who first brought water to a people provided a mythical blueprint, a precedent that human engineering could aspire to fulfill. It legitimized the staggering cost and effort by framing it as the continuation of a divine purpose. The aqueduct became more than a civic work. It was a collective act of piety, a way for the entire community to participate in a miracle once reserved for deities. This fusion also reflects how these societies perceived their own technological prowess. The boundary between inventing a siphon and performing a miracle was thin. When the engineer Eupalinos completed his kilometer-long tunnel on Samos, the achievement was so extraordinary it likely felt supernatural to his contemporaries. In the absence of our modern scientific worldview, such a feat could easily be woven into the existing tapestry of myth, perhaps credited to the favor of Athena, the goddess of wisdom and craft. Myth did not hinder technology, it gave it meaning and cultural permission. It answered the why as much as the how. By examining this intersection, we see that an aqueduct was never just a conduit for water, it was a conduit for belief. It channeled a society's deepest understandings about its place in the world, its relationship with the capricious forces of nature, and its own burgeoning power to reshape destiny. The stones carried not just liquid but the weight of story, transforming a mountain spring into a legend that flowed straight into the city square. The Pont du Gard does not simply cross a river, it commands the valley with a silent, rhythmic poetry. Its 3 tiers of arches are a masterclass in visual harmony, each level perfectly proportioned to the one below, creating a structure that feels both immense and impossibly graceful. This beauty was not an accidental byproduct. It was a deliberate architectural choice, a language spoken in stone that reveals how deeply aesthetics were woven into the very purpose of these gravity-defying channels. The engineers understood a profound truth: for something built to last 1,000 years and to be seen by every traveler for generations, form could not be separated from function. The principles they followed were both mathematical and artistic. The rhythmic repetition of the arches creates a visual cadence that guides the eye across the landscape, a stability that subconsciously communicates strength and order. The piers, the vertical supports, are not uniform blocks. They widen at the base in a subtle taper, a technique that makes the structure appear rooted and immovable against the current and the centuries. Even the protruding stone brackets that once supported the scaffolding for construction were left in place, not as unfinished clutter, but as a textured pattern that catches the light and adds a layer of human scale to the monumental facade. This attention to visual detail extended to often overlooked spaces. The spandrels, the triangular areas between the arches, were sometimes adorned with simple geometric carvings or inscriptions naming the emperor and the legion that built it. These were not hidden signatures but public proclamations of ownership and achievement, turning the aqueduct itself into a permanent billboard for imperial power and civic benevolence. The setting was chosen with a painter's eye. The Pont du Gard was not placed at the narrowest point of the river, but at a spot where the rugged limestone cliffs framed the structure, making it a dramatic focal point in the natural amphitheater. This strategic placement amplified its visual impact, ensuring that anyone approaching would feel a sense of awe, a visceral understanding of the civilization capable of such a feat. But what purpose did this beauty serve beyond admiration? It fostered a deep, emotional civic pride. A structure that inspired wonder was a structure worth protecting. The local community, seeing this elegant giant as a symbol of their connectedness to Rome and a source of their own prosperity, would be more likely to report cracks or sabotage, to support the taxes for its upkeep. The aesthetics encouraged a sense of shared guardianship. Furthermore, the visual harmony had a subtle psychological function for the Romans themselves. The aqueduct, in its serene proportionality, represented the ultimate triumph of human reason over chaotic nature. Its beauty was the beauty of logic made visible, of mathematics translated into enduring stone. It reassured the citizen that the world was orderly, that the state was competent, and that the future was secure. This fusion of utility and art is what elevates these structures from mere engineering to enduring cultural landmarks. They were not hidden infrastructure, they were celebrated monuments. The water flowing across the top was the lifeblood, but the arches below were the beating heart of civic identity. The ancients valued the experience of their infrastructure, the way it shaped the landscape and the human spirit, as much as the clean water it delivered to the public fountains. In their world, the true measure of a civilization was not just what it built, but the grace with which it built. That grace came at a staggering price, a cost measured not in coins, but in the redirected wealth of an empire. Building an aqueduct was the ancient equivalent of a modern moonshot, a decades-long financial commitment that required marshalling resources on an almost unimaginable scale. The funds to carve mountains and stride across valleys did not materialize from thin air. They flowed from a complex economic ecosystem designed to turn imperial ambition into flowing water. The primary source was the imperial treasury itself, the fiscus, filled by taxes levied across the provinces. An emperor like Claudius or Trajan could simply decree a new aqueduct and allocate the vast sums required, framing it as a direct gift from the ruler to his people. This was state spending at its most visible, a powerful political statement that the government's role was to provide monumental public goods, but another common and highly symbolic source was war booty. The conquest of a wealthy region would flood the treasury with captured gold, silver, and tribute. Channeling this plunder into a permanent, life-giving structure within Rome was a brilliant act of political alchemy. It transformed the spoils of violence and subjugation into an engine of civic peace and health, laundering the wealth of defeated enemies into the pure water of Roman baths. For the elite, funding an aqueduct or a major fountain was a path to immortal prestige. Wealthy senators or successful generals, seeking to cement their family's legacy, would often donate vast sums for a specific section or a decorative terminal fountain, a nymphaeum that would forever bear their name. This was philanthropy as a competitive sport, with the public good as the ultimate trophy. At the local, municipal level, the burden sometimes fell on the city council and its citizens, funded through local taxes or the fortunes of leading townsmen. A remarkable window into this financial machinery comes from a series of inscriptions related to the Aqua Augusta, the aqueduct serving Naples and surrounding towns. These stone receipts, carved for public record, break down costs with bureaucratic clarity. They list payments for specific materials, so many thousand bricks at a set price per thousand, so many loads of volcanic sand for mortar, and contracts for skilled labor like the aquelects, the master well digger, paid by the foot of depth. We see allocations for the upkeep of the work camps, money for food and tools. This granular accounting reveals an economy in motion, from the quarry owner and the brickmaker to the day laborer, all linked by the river of silver that funded the river of stone. So what was the return on this colossal investment? The dividends were measured in the quiet absence of crisis. Public health was the foremost yield. A reliable, clean water supply drastically reduced waterborne illnesses, leading to a more productive, stable population. Economic activity surged. Water-powered mills for grinding grain, supplied tanneries and fulleries for cloth production, and irrigated market gardens on the city's outskirts. The construction project itself was a massive economic stimulus, employing thousands and creating demand for materials and transport for years. But perhaps the most valuable return was political stability. A well-watered city was a content city. The public baths provided hygiene and recreation, the fountains offered free access for all, and the very spectacle of the aqueducts was a daily reminder of the state's power to provide. It built what we might call hydraulic legitimacy, the consent of the governed, earned not just by law but by the tangible, life-sustaining flow from the taps. This financial commitment reveals a profound ancient truth. Water security was not a utility. It was the ultimate public trust. The redistribution of wealth from treasury, from conquest, or from private fortunes into these stone channels was a civilizational wager, a bet that the greatest security and prosperity came from investing not in walls but in water. The aqueduct was a neighbor long before it was a monument. For the farmer tending his vineyard in the shadow of its arches, the structure was a familiar giant, a part of the landscape as constant as the hills. Its steady hum was the sound of the city in the distance, a reminder of a world beyond the fields, yet its presence shaped daily life in countless quiet ways. The land beneath and around the soaring arcades became new, ambiguous space. Shepherds found shade for their flocks in the perpetual coolness under the arches. Travelers used the endless, straight embankment as a raised pathway, a dry road in wet seasons. The aqueduct did not just pass through the countryside. It created a corridor of human activity along its entire length, a stone spine with a life of its own. Where the water finally emerged into the city, it transformed public space completely. The endpoint was never a hidden pipe but a celebration. The public fountain, or lacus, was the neighborhood's living room. Here, people of all ages and classes intersected. Women and servants filled clay jars, exchanging the day's news. Children played in the overflow. Men gathered to discuss business or politics. The fountain's constant, clean flow was a democratizing force, a guarantee that no citizen would go thirsty. It was more than a utility point. It was a social anchor, a symbol of shared civic fortune. The grander nymphea, ornate fountain houses adorned with statues and mosaics, served as magnificent backdrops for public life, turning the act of drawing water into an experience of beauty and imperial grandeur. This infrastructure actively drew people toward it, reshaping where and how they lived. Settlements naturally clustered along reliable aqueduct routes, and new suburbs called vici sprang up around major distribution points outside the old city walls. The promise of water made these areas desirable, easing urban crowding and creating new communities whose very existence was tied to the engineered flow. The public baths, those vast complexes consuming enormous volumes of water, became the ultimate social hubs. For a tiny coin, a citizen could spend hours in a sequence of heated rooms, cold plunges, and swimming pools. It was a place for exercise, conversation, business deals, and intellectual debate. The baths were a great social leveler, where the poor could access the same basic hygiene and leisure as the wealthy, all thanks to the aqueduct's endless gift. But this shared resource was also a source of friction. Legal codes and the writings of officials like Frontinus are filled with complaints about water theft. The wealthy, whose homes were plumbed with private lead pipes branching from the main lines, were constantly tempted to install illegal taps or enlarge their official pipe diameters, stealing water meant for public use. This was not a minor offense, it was seen as stealing from the community itself. Frontinus describes his teams hunting for these clandestine diversions, sometimes finding pipes hidden in walls or buried deep underground. The conflict between public utility and private privilege was a constant undercurrent, a quiet battle over who truly owned the mountain's gift. Graffiti scratched into the plaster lining of aqueduct channels or on fountain basins adds a deeply human voice to this story. These are not official inscriptions but spontaneous marks. A traveler might carve his name and the date, claiming a moment in the flow of time. A worker might leave a simple tally mark or a crude drawing. This casual vandalism, preserved for millennia, reminds us that people lived and worked in intimate contact with these structures. They were not distant wonders, but parts of the landscape to be touched, used, and sometimes defaced. The aqueduct's greatest legacy, therefore, may not be in the engineering, but in the experience it crafted. It defined the rhythm and quality of urban life for centuries. The morning trip to the fountain, the afternoon at the baths, the evening stroll past a flowing nymphaeum, these were rituals made possible by the silent river in the sky. It fostered a sense of collective identity and civic pride, a tangible connection between the individual and the immense, organized power of the state. For the ordinary person, the genius of the aqueduct was not measured in gradients or siphons, but in the full jar of clean water, the laughter of children by the fountain, and the profound, everyday security of knowing the flow would never stop. This was the human magic, turning hydraulic engineering into the very pulse of community life. The sound of a collapsing arch was the sound of a city holding its breath. For all their monumental strength, aqueducts were fragile lifelines, vulnerable to the very forces they were built to defy. A single catastrophic flood could undermine a bridge pier, an earthquake could shatter a pressurized siphon, or a prolonged siege could see an enemy deliberately cut the channel. These were not hypothetical risks, they were historical realities that forced societies to adapt or retreat. The story of water is also a story of its sudden, terrifying absence. During the Gothic wars of the 6th century, the besieging armies repeatedly severed the aqueducts leading into Rome. The once mighty channels, symbols of eternal order, were weaponized against the population they sustained. Without the constant flow, the public fountains fell silent, the great baths became hollow shells, and the city's sanitation system ground to a halt. The populace, which had swelled to over 1 million, was forced into a desperate scramble. They returned to the ancient, forgotten springs within the city walls and deepened old wells, but these sources were utterly inadequate for such a dense population. Districts farthest from the Tiber River became unsustainable, and people crowded into lower, riverside areas, fundamentally altering the urban map. Rome did not fall in a day, but its aqueducts did, and their failure accelerated a centuries-long contraction from a metropolis of marble and water to a more medieval, fortified town clustered around the river's edge. This pattern repeated across the empire. In North Africa, magnificent aqueducts supplying cities like Carthage were damaged by Vandals and never fully restored by the Byzantine reconquest. The complex, centralized system proved too brittle without the imperial bureaucracy and funding to maintain it. The response was not a grand rebuilding, but a pragmatic devolution. Communities learned to think smaller. They invested in local cisterns to capture rainwater, repaired ancient springs, and built modest, kilometer-long channels from nearby hills instead of 100-kilometer conduits from distant mountains. The grand vision of a single, gravity-defying river feeding a city was replaced by a patchwork of local solutions, a return to hydrological self-sufficiency. In some places, the failure was environmental. There is evidence that in parts of the Roman province of Syria, ambitious irrigation and aqueduct projects may have contributed to a rise in the local water table, bringing salts to the surface and slowly poisoning the soil with salinity. The land over centuries became less productive, undermining the agricultural surplus that supported the urban centers the water was meant to supply. It is a stark lesson in unintended consequences where solving one problem, delivering water, gradually created another, degrading the very land that grew the food. These failures teach a sobering lesson about complex infrastructure. An aqueduct was not a standalone object. It was the most visible part of a vast, interdependent system. Its health required political stability to fund repairs, technical knowledge to train new generations of aquarii, and a peaceful countryside to protect its miles of exposed channel. When those social and environmental conditions fractured, the engineering marvel became a monumental liability. The vulnerability was not in the stone, but in the civilization that built it. A broken aqueduct is a fossil of a broken contract, a reminder that our greatest technological achievements are not permanent victories, but careful balances, sustained only by continuous care, collective will, and a stable partnership with the world they alter. The very word we use to describe these stone rivers carries their echo. Aqueduct, from the Latin aqueductus, literally means a leading of water. This was not just a technical term. It was a concept that began to shape how people thought about control and direction. To have an aqueduct was to possess the power to lead a necessity from its source to a chosen destination. Over centuries, this physical idea seeped into our abstract vocabulary. We speak of channels of communication, of directing the flow of information, of intellectual conduits. The metaphor is so deeply embedded we forget its origin in those gravity-defying channels of stone. The technology gave society a new mental model for organization itself, a way to visualize the deliberate, guided movement of anything vital from one point to another. But the Romans did more than give us a word. They built an entire legal framework around the water it carried. Water law was not an afterthought. It was the essential operating system for the aqueduct's promise. The fundamental principle, established early and enforced ruthlessly, was that flowing water was a public resource, a res publici. It belonged to the people, and its use was governed by the state for the common good. This was a revolutionary concept that placed community need above individual desire. The legal codes, meticulously detailed by officials like Frontinus, addressed every conceivable conflict. The right-of-way for an aqueduct was sacred and permanent. If the surveyor's line crossed your farm, you could not block it. You were compensated for the land, and the state's easement was absolute. This legal power to reshape private property for public utility was a staggering assertion of state authority, one that modern governments still wield for pipelines and power lines. Pollution was a serious offense. The law forbade dumping waste or diverting dirty runoff into the channel. Farmers upstream could use the water for irrigation, but only if they returned it undiminished in quality and quantity to the main channel downstream. This recognized the interconnectedness of a watershed, a remarkably early form of environmental regulation. The most common crime, and the one that filled the court dockets, was water theft. Tapping into a public aqueduct without a license was not a minor misdemeanor, it was theft from the entire citizenry. The penalties were severe, involving heavy fines and sometimes public disgrace. Frontinus describes his teams acting as hydraulic detectives, measuring flow rates at different points to find discrepancies that pointed to an illegal tap. The law even specified the permissible size of pipe that could connect to the main line, with larger diameters requiring special, expensive permits typically only affordable by the wealthy or for public baths. This created a tension between law and privilege that was never fully resolved. The legacy of this legal architecture did not crumble with the aqueducts. The core Roman principle that water is a public trust profoundly influenced later European legal codes, from the Napoleonic Code to English common law. The idea that a river could not be wholly owned by a single landowner, that it had a public character, stems directly from these ancient statutes. Our modern debates about water rights, pollution control, and public access to resources are still conducted on a foundation laid 2,000 years ago. The aqueducts taught civilization a lesson in scale, that managing a resource on which millions depend requires not just engineering, but a robust and fair system of rules. The stones channeled water, but the laws channeled human behavior, attempting to direct the flow of society itself toward the common good. This subtle imprint in our language and our courts may be their most enduring triumph, a current of thought that continues to flow long after the last arch has fallen. A digital river now flows where only ruins remain. With a headset or a screen, you can stand inside the Aqua Virgo as it looked in the reign of Augustus, hearing the water rush through a channel of pristine travertine, watching sunlight filter through arches that have not crumbled. This is not a video game, it is a new form of historical dialogue powered by virtual and augmented reality. These technologies are doing something revolutionary. They are turning data points into lived experience. By feeding archaeological surveys, drone scans, and ancient texts into sophisticated modeling software, researchers can rebuild an entire aqueduct system from the subterranean spring to the final public fountain. You can follow the Aqua Virgo's entire 22-kilometer course in minutes, watching the landscape transform from rural springs to the bustling heart of ancient Rome, all while the precise gradient of the channel is calculated and visualized in real time. This digital resurrection serves a profound scientific purpose. Archaeologists can use these models to test long-standing hypotheses in a risk-free environment. They can simulate different construction sequences, asking what happens if you build the bridge before digging the tunnel, or they can adjust the virtual channel slope by a fraction of a percent to see how it affects water speed and sediment buildup. Computational fluid dynamics software can be integrated into the model, showing exactly how the water behaved, where eddies formed, and how much pressure built up at the bottom of an inverted siphon. These virtual experiments answer questions that physical ruins cannot, revealing the aqueduct not as a static monument, but as a dynamic, working machine. But the impact goes far beyond academic testing. The true magic of this digital walkthrough is emotional and cognitive. Reading that an aqueduct dropped only 30 centimeters per kilometer is a fact. But virtually standing in that channel and looking ahead as it stretches into a barely perceptible descent makes you feel the engineer's intention. You grasp the patience, the scale, and the quiet confidence of that gentle, unwavering slope. It transforms an abstract principle into a sensory truth. For students and the public, these tools demolish the barrier between the present and the past. Augmented reality apps allow you to point your phone at a fragment of a lone arch in a modern park and see the complete structure superimposed on the landscape, understanding its original height and context. This bridges a critical gap. It turns a confusing pile of old stones back into a legible piece of a city's anatomy. The past stops being a separate country and becomes a layer of our own world waiting to be uncovered. This digital preservation is also an act of defiance against time and loss. For structures threatened by modern development, pollution, or the slow creep of erosion, a perfect three-dimensional scan becomes an eternal record. Even if the physical stone succumbs, its precise digital twin survives for future generations to study and explore. These virtual reconstructions do more than show us what was, they teach us how to see. They train us to look at a barren field and perceive the hidden geometry of a buried conduit, to hear in the silence the ghost of a flowing river that once sustained an empire. The experience reshapes our understanding from the outside looking in, to something far more intimate, the feeling of walking in the footsteps of the liberator as he squints along his chorobates, tracing a line of water across an unborn world. Steel and concrete now carry the same ancient ambition. The California Aqueduct is a modern spine of civilization, a 700-mile-long concrete channel that pushes water from the wet north to the thirsty cities and farms of the south. It is a descendant of the Roman model in both scale and purpose, but its tools are different. Where Roman liberators used chorobates, modern surveyors use satellite-guided lasers. Where Romans relied on gravity alone, this system employs a chain of massive pumping stations like the Edmonston pumping plant, which lifts water nearly 2,000 feet over the Tehachapi Mountains. That single lift requires more power than the entire city of San Francisco, a staggering energy cost the Romans never faced. Yet the core challenge is identical. How do you convince a river to flow against its geographic destiny? In China, the South-North Water Transfer Project is an undertaking of almost incomprehensible scale, aiming to move trillions of gallons of water from the Yangtze River basin to the arid north. Its eastern route uses the ancient Grand Canal, a waterway first built in the 5th century, demonstrating how modern projects often layer upon the bones of past ingenuity. The central route, however, involves tunneling beneath the Yellow River itself, a feat of pressurized engineering that would make a Roman builder of inverted siphons nod in recognition. The water in those deep tunnels is under immense force, held not by lead pipes but by steel and polymer linings. Yet the principle of contained pressure to push water through an obstacle is a direct technological error. Even in renewable energy, the ancient siphon finds new life. Pumped storage hydroelectric plants are essentially giant, reversible inverted siphons. During times of low energy demand, electricity is used to pump water from a low reservoir to a high one. When demand peaks, that water is released, rushing down through turbines to generate power. It is a battery made of gravity and water, a sophisticated echo of the same potential energy the Romans harnessed in a simpler form. The scale of these modern projects dwarfs the ancient world, but the societal goals are strikingly familiar: to enable agricultural abundance, to fuel urban growth, and to secure political stability by controlling the most vital resource. The environmental conversation, however, has grown more complex. Roman engineers altered local watersheds with profound effects, but their world lacked our scientific understanding of ecosystems. Today, we see the consequences of large-scale water transfer with greater clarity, from the sinking of land due to aquifer depletion to the disruption of fragile habitats. The modern parallel forces a difficult question: have we simply exchanged one set of limitations for another? Ancient systems were constrained by material strength and survey precision. Ours are constrained by energy cost and ecological impact. This comparison offers a crucial lesson for today's project managers, one of perspective. The Roman aqueducts that still stand did so because they were built for permanence, with over-engineered materials and a deep integration into the landscape. They followed the land's logic as much as they conquered it. Some modern infrastructure built for efficiency and speed can lack this longevity. The ancient approach whispers a reminder: to build something that lasts 1,000 years, you must think in centuries, not fiscal quarters. You must see the project not as a line on a map, but as a new organ in the body of the landscape, one that must function in harmony with the geology, climate, and life around it for generations. The gleaming concrete channels and humming pump stations of our era are the latest verses in a very old song. They prove that the impulse to move water is a constant in the human story, a response to the same arid threats and crowded opportunities. The tools evolve, but the fundamental defiance of gravity, that stubborn refusal to let geography dictate destiny, remains unchanged. It is a testament to an unbroken lineage of problem-solving, where every modern engineer stands, consciously or not, on the shoulders of those who first taught water to climb. A public fountain promised water for all, but the pipes told a different story. The Roman aqueduct was a triumph of public engineering, yet it flowed through a society built on sharp distinctions. The legal principle was clear: water was a res publici, a public thing. In practice, its distribution mirrored the city's social pyramid. At the base were the countless lacus, the simple street fountains. These were the lifeline for the vast majority, the poor, the enslaved, the ordinary citizens. Anyone could approach with a clay jar and fill it with cold, clean mountain water, entirely free of charge. This was a revolutionary guarantee of basic dignity, a state-provided safety net that prevented thirst from becoming a tool of desperation. One tier up, the reality shifted. Wealthy homeowners could apply for a license, paying a substantial fee to the state for the ius aquae, the right to water. This granted them a private lead pipe, a fistula, that branched from the main channel directly into their villa. This pipe delivered water under pressure, enough to supply a small courtyard fountain, a kitchen, and sometimes even a private bath. It was a convenience that removed the daily chore of fetching water, a marker of status as clear as the marble on their walls. At the very apex stood the emperor and the state itself. The most lavish allocations fed the imperial palaces, the sprawling public baths that bore the emperor's name, and the monumental nymphea. These ornate fountain houses, adorned with statues and mosaics, served a dual purpose. They provided spectacular public amenities, yes, but they also displayed the emperor's godlike generosity and control over nature itself. The water flowing there was a performance of power. The system's administrator, Frontinus, framed this not as inequality but as ordered priority. In his treatise, he lists the hierarchy of needs, first for public health and safety, then for public delight, and lastly for private license. The system was designed to prevent the public good from being completely usurped by private greed, though the constant complaints about illegal taps prove that greed was a persistent opponent. This ancient arrangement holds up a mirror to our own world. Today, the question of water equity is not about public fountains versus private pipes, but often about pipes versus no pipes at all. In countless modern cities, from sprawling metropolises to growing towns, infrastructure maps can look like a diagram of historical inequality. Wealthy neighborhoods often have newer, well-maintained water mains, reliable pressure, and advanced treatment. Less affluent districts might suffer from century-old, lead-lined pipes, frequent service interruptions, or water priced at a rate that strains household budgets. In some places, the challenge is even more fundamental: a complete lack of centralized infrastructure, forcing reliance on expensive trucked-in water or untreated well water that carries health risks. The Roman model forces us to ask a difficult, enduring question. When we engineer a solution to a universal human need, how do we ensure it truly serves all? They established a baseline of access with their public fountains, a floor below which no one should fall. Our modern conception goes further, framing clean water not just as a public service, but as a fundamental human right, as recognized by the United Nations. This shifts the ethical obligation from charity to justice. It means the responsibility of a society is not merely to provide water, but to provide it in a way that is safe, affordable, accessible, and sufficient for every person without discrimination. The aqueduct, as a centralized system, also warns us of a subtler form of exclusion. When a city sources its water from a distant mountain watershed, it is making a choice that benefits the urban population at the potential expense of the rural communities at the source. The Romans did this with little regard for the downstream effects. Today, we see similar dynamics in large-scale water transfers that can drain rivers and lower water tables in agricultural regions to fill the reservoirs of distant cities. The technological advance creates winners and losers, often along geographic and economic lines. So what responsibilities come with controlling the spigot of civilization? The ancient answer was a blend of civic duty, legal enforcement, and political display. Our answer must be more holistic, weighing engineering prowess against environmental stewardship and social justice. The quiet lesson of the Roman pipe is that technology alone cannot solve the problem of equity. It can deliver the water, but only a conscious, collective commitment to fairness can decide who gets to drink. As we build our own vast networks of pumps and pipes, we are continuing that ancient debate, deciding with every policy and investment what kind of civilization our water will flow toward. A crumbling stone arch holds more than just the memory of water. These ancient conduits now face a slow, modern siege, not from armies, but from the very air we breathe and the world we have built. Acid rain, born from industrial and automotive pollution, eats away at limestone and mortar with a patience that rivals their builders. In cities that have grown for centuries around them, vibrations from subway lines and heavy traffic send invisible tremors through foundations never designed for such constant strain. The gentle kiss of lichen and moss, once a slow natural process, can accelerate with changing humidity, prying apart meticulously fitted stones, and climate change introduces a new, unpredictable adversary, with more intense freeze-thaw cycles cracking stone from within and extreme weather events testing millennia-old drainage. The Aqueduct of Segovia, that breathtaking silhouette against the Spanish sky, endures a constant battle against time and traffic. Its granite blocks, once thought eternal, now require meticulous monitoring for stress fractures caused by the vibrations of a modern city living in its shadow. Preservation is no longer a passive wish, it is an active, urgent science. The tools of this new defense are a blend of ancient craft and space-age technology. Conservators might use traditional lime mortars, mixed to match the original composition, to repoint stones without causing chemical damage. But they also employ 3D laser scanning to create millimeter-perfect digital models, allowing them to detect the slightest shift in the structure's posture over time. Ground-penetrating radar checks the health of hidden foundations, and drones inspect the highest arches for cracks invisible from the ground. The work is painstaking and expensive, a global effort supported by a framework of laws and international recognition. National heritage laws protect these monuments from demolition or insensitive development, while UNESCO World Heritage status, granted to sites like the Pont du Gard and the Segovia Aqueduct, provides not just prestige but a commitment from the global community to safeguard them. This status can unlock vital funding and expertise for conservation projects that might otherwise be beyond the reach of local authorities. Yet, legal protection is only as strong as the will to enforce it and the resources to back it up. So what truly vanishes if a single arch falls, if a channel silts over forever? We lose more than a picturesque ruin. We sever a physical tether to a moment when humanity first conceived of infrastructure as a century-spanning covenant. These stones are the original textbooks of civil engineering, of fluid dynamics, of project management. To let them decay is to erase a primary source, to turn a tangible lesson into an abstract footnote. Future generations would know of aqueducts only from drawings and descriptions, never feeling the awe of standing beneath their scale, never tracing the groove worn by 2,000 years of flowing water with their own hand. That direct sensory connection sparks a unique kind of understanding, a humility and inspiration that no digital model can fully replicate. Preserving them is an act of cultural memory, ensuring that the foundational chapter of our shared technological story remains legible, not as a myth, but as a mountain of stone that still defiantly stands. The Siphon's secret and the Surveyor's unwavering line trace a single, profound narrative of human aspiration. We have followed water's impossible journey from mountain spring to city square, uncovering the three silent principles that made it flow, the civilizations it sustained, and the quiet mysteries it left behind in crumbling stone. This story is not merely about moving water, it is about moving possibility. It reveals a timeless pattern where immense challenges are met not with magic, but with meticulous observation, stubborn collective will, and a creativity that patiently converses with the laws of the natural world. Our ancestors looked at a mountain and saw not a barrier but a path. They studied a flowing river and understood it could be reasoned with, persuaded, and guided. Their legacy is carved in more than limestone and travertine. It is etched into our very concept of public good, into the legal frameworks that govern shared resources, and into the enduring belief that a society's greatness can be measured by what it builds for all its people. So the next time you turn on a tap, pause for a moment. That simple, reliable flow is the end point of a conversation that began over 2,000 years ago, a conversation about defying gravity, geography, and time itself. It represents millennia of accumulated ingenuity, a current of thought that has never stopped flowing. If this journey into the heart of ancient engineering resonated with you, consider subscribing for more deep dives into history's greatest puzzles. And let us know in the comments which other gravity-defying marvel or lost technology should we explore together next.